Hello, everybody, and welcome to the third part of our series of presentations on GPS GNSS testing. This week, we're going to look at interference and robust PNT and those kind of things. So if I move on, we'll look at the agenda. Okay, so the first part is a quick description on robust PNT, and my colleague from Aurelia, Jeremy Thomas, is going to introduce that. Then we'll have then I'm afraid you're back to me, and we'll have a section on interference, jamming, and resilience testing. Then we're going to look at spoofing testing, and then we'll have a summary at the end. It is quite a big subject. We're going to look at it from a high level, really, but hopefully this will be interesting and help you wanting more. So I'll pass over to Jeremy here, and he can talk to you through these slides, and then we'll go from there.
Yep, thank you, Andy. Morning, everybody. So yes, I'm Jeremy Thomas, Aurelia Business Manager for the UK and Northern Europe. So yeah, I work closely with Andy and the Hydra team on simulation. And today, just a few slides from myself to provide a brief introduction on the world of resilient PNT and its environment, which leads nicely into the GNSS simulation and test focus, which is core to today's webinar. In essence, GPS and now the collective term GNSS receivers are prolific, and use is increasing across air, land and sea applications. So mobile and static, government and commercial. It is a primary sensor in the PNT, which is position, navigation and timing of critical systems. So with this in mind, we think about infrastructure and assets. They can have their GNSS challenged or even be in denied environments, so physically restricted. So for denied, you can think of tunnels, buildings, mountains, weather and such like. So we need to see the good signals, yet be able to survive if challenged. Challenges can be intentional, jamming and spoofing, or unintentional interference. So the RF world is a busy place, and it's only getting busier. Either way, it's essential to understand the threats, test the receivers and the platforms and software they are integrated into, and then put mitigating measures in place so we are prepared for all eventualities. Next slide, please. Thank you. So the approach to resilient PNT. In the core, we have a GNSS receiver platform. Integral to these will be oscillators for timing, and some will incorporate additional local sensors, such as inertial measurement units, commonly referred to as IMUs. To the top left, there's the RF side of a PNT platform to understand GNSS and optimize its use and resiliency through interference detection and mitigation, often referred to as IDM techniques. Top right, you've got resiliency on the network. So network timing, NTP, network time protocol, PTP, SYNC, White Rabbit, IP-based monitoring and control. The connection of integrated devices is proliferating, so protecting it, testing it, and certification are all critical elements. Then at the bottom here, there is sensor fusion as well as alternative signals of opportunity. So augmenting GNSS with other signals, be they terrestrial or space-based. So here, things like low Earth orbit, LEOs, ELORAN, pseudolights, SBAS, even local tachometers, compasses and such like. Finally, elements such as encryption and secure signals. All of these coming together. There's no one solution to resilient PNT. So a key point is that GNSS, however, remains today and will remain for many the primary PNT reference. So the simulation is critical. Remember, GNSS includes multiple constellations to access. It is globally available. It is wireless, so it covers mobile applications, and it is free at the point of access. Next slide, please, Andy. So now on to the resiliency part. An important question to ask yourself for RPNT is what do you want or need to do? Here we take a three-layered approach. So detection, you want to be aware once you know that your primary reference is compromised. From a point of detection, you can then access an alternative or secondary PNT service. If you don't know this and in detail, you cannot take action. So that detection piece. Secondly, protection. You want to combat or reduce the threat. You may want to provide access to alternative PNT services that you do not currently have. Here you want to try to define the characteristics of this secondary service: precision, stability, accuracy, traceability, maximum duration of the primary PNT service outage. And then finally, data collection and analysis. So you want to characterize, visualize, or document the threat. What is it? Where does it come from? Visualization through heat maps, monitoring of the quality of PNT service, recording, forensics, both in real time or over a period. Knowledge is power, as they say. Next one, please. Then finally, for me, just to touch on Arolia's core RPNT platforms. So alongside simulation, it is a primary technology sector we lead in. On the embedded side, we have three principal resilient PNT platforms. And just cover this very briefly, we've got the Secure Sync. So for static, highly configurable time and frequency synchronization and distribution. This is our primary modular, customizable COTS platform, ruggedized, configurable, resilient, and cyber secure. This is deployed across all markets and applications, basically large enough where a rack can go. VersaSync, essentially a secure sync in a compact package for mobile and harsh environments. So anything smaller than a rack or much more mobile and moving around, be it UAVs, cars, trains, ships, you name it. And then finally, the Versa PNT. So this is taking the VersaSync and adds positioning and navigation capabilities, so IMUs and other sensor fusion. So that's enough for me today, but I will be happy to take questions and discuss with anyone further on the RPNT part after this session. Just get in touch with me. Thank you.
Thank you, Jeremy. And right, we're back to me now. So first of all, just a quick overview of resilience and what is the effects on PNT or on navigation or on GNSS from these different conditions. So first of all, you have sort of things like spoofing, where people are giving you a fake signal for some reason or other, maybe wanting to put you somewhere else, or possibly just accidental with a signal spillage. Then you've got jamming, where someone uses interference. Again, it can be intentional or quite unintentional, but these things can happen, and then that will upset the GNSS performance. Then you have potential errors within the GNSS system itself. Uploads have been wrong. This has been known. Satellite errors. There was a problem with satellite number 49 back along. Different things like that. And again, these are risks, areas of risk. Atmospheric conditions, solar maximus, causing things like heating of the upper atmosphere, which will cause bigger delays in the signals and bigger refractions, and so potential timing and positional errors. Or scintillation, where you get very local effects, which can cause quite big changes. Cyber attacks, maybe you're relying on some assistance data, and someone might affect that data, which will cause problems for you. And then of course multipath, buildings blockages, all sorts of things within the local environment which cause problems, due to obstruction of the signal or reflection of the signal locally. Okay, so we'll move on, and we're going to talk about jamming, okay, or interference, or whatever you want to call it. So first of all, the first thing to really understand is that GPS signals are incredibly low power, very, very weak, approximately 1/trillionth of a watt, minus 130 dBm. You compare that to something like a mobile phone at minus 70. That's quite a big difference in power. Every 30 dBs is 1,000 times difference in power. You got minus 30 there, something like a Wi-Fi hub or something. And, these are similar frequencies, GPS is L1 is 1575.42, megs. LTE up around 1.8, 1.9, so 1800, 1900. Wi-Fi up around 2400, 2.4 gigs. So these are quite close proximity. A microwave oven, for example, usually those are running at 2.4 gigs as well. And that's 1,000 watts. That's a lot of power. And then maybe something like an FM transmitter, off frequency somewhat, but still massive power and can cause problems. So the signal strength is very weak, and it's operating in this environment with all these other signals around. It's difficult anyway, and these things can cause problems accidentally. So these are things to watch for. Also, there's been a proliferation of what's some privacy devices, jammers in cars, GPS receiver in a vehicle. Quite often people put jammers in. When a few years ago I was talking to a guy who ran a fleet, and he was saying that they were changing their system because only about half of their system worked, and they were buying a new system because they were having problems with the old. And I said to him, you'll probably find only half of them will work when you buy the new system. And he was quite shocked to hear that. And I said, problem probably isn't the system. The problem is probably that some of your drivers don't want you tracking them, and they've got devices like this in their cab. So these things they're around. They're maybe not so easy to get hold of these days. They're totally illegal to use, but the way they're advertised and presented, they sound like they're just fine. They're only going to affect yourself and things like that. It's a relatively simple waveform. It's relatively easy to test them, but to test the effects of them, but they can be quite effective. Okay. Other jammers, you could be jammed by a car sitting next to you with one of these things in. Signal power, Doppler, or dynamic, and they can change and cause problems. So all these things need to be checked how you cope. Then you'll have things like unintentional jamming. So microwave dishes, transmission masts, something like this. They will be broadcasting signals. They can cause problems in the L band. Quite often some of these are L band anyway, and I've seen incidents where they've caused problems for GPS receivers, in close proximity. Things like cell towers have caused problems for GPS. So it's it can happen. It's not the direct frequency coming from that transmitter, but you get what they call harmonics, and when you're down at minus 130 dBm, even a third or fourth harmonic can cause problems from a high power signal. Okay, they can be quite intermittent, they can be quite short in period, they can last a long time, and sometimes they might only occur at certain times. Maybe when your cell tower is busy and it switches to more frequencies, and that causes some issues. You need to have quite a flexible approach to testing, and actually detection of these things are quite hard. And then of course you've got warfare, where you've got someone trying to put you off so that you can't attack them, or that you lose your navigation, your troops get lost, or quite often these days to stop your communications. If you lose timing sync, you can't talk to people. So warfare, there's a lot of jamming goes on there to stop people. Okay. So within our system, we have two types of jamming. We have what we call simplified jamming and dynamic jamming. So simplified jamming is just a simple waveform, something like a CW or a chirp signal. You choose a power level, you configure it, and off it goes. It just creates that signal, and then you can obviously switch it on and off, and you can see how that affects your receiver. But generally, it's not a lot of control. It's just put a jammer on, take a jammer off, see what your receiver does. It's not particularly realistic, but it does help you understand, how these things might affect your receiver. And then we have what we call our advanced jamming, which gives you much more capability. So you can create one or multiple transmitters. You can locate them on a map as you move towards them, so the power will go up. As you move away, the power will go down. You can create more or less complex waveforms by lots of different signals. You can even put in your own waveforms. And they allow you to do much more realistic, much more like you'd see in the real world type jamming, and see how your receiver copes with those capabilities, those situations as well. Just this is just to give you a rough idea of how jamming can change. If you see, this is a sort of simulated vehicle going along. Here's the jammer with power. You can see main point of power is coming out this way. So as this vehicle moves along, you can see the signal is weaker here as it gets in the beam of the jammer, so it gets much stronger. And then as you move away, so the power reduces again. And that's the kind of effects that you want to be able to see. And what you'll be looking for is, at what point when the power goes up, does your receiver drop out? And then as the power goes down, at what point does your receiver lock back on again? And how does it affect the accuracy? So as the power is going up, how does it affect the accuracy of your receiver? And then as the power goes down, when it locks on, how accurate is it? And then how quickly does it sort of get back to where it should be? Jamming, why is J2S important? Well, the J2S, jammer to signal, is the measure that you often see, and the higher, obviously, the J2S, the more it will affect your receiver. But as you can see from this chart here, the power drops quite quickly as you move away from the jammer. But and so this is what's known as the inverse square law, and power will drop off quite quickly, but it still has an effect. And even at these lower powers, there is an effect. It will lower the jammer to signal level, and a receiver, if it's seeing in the real clear sky, a GPS satellite, you'll probably see a receiver something like a U-Blox log something around 40 dBs jammer to signal. If that number starts to go down because there's a jammer in the distance, it will make it harder for the receiver to lock on. Usually if it goes below about 30, you will find that it's much harder for the receiver to lock on, and you'll find that it's less accurate when it does lock on. Also, if you've got jammers in one direction, it will cause an effect on the receiver in that it will block satellites from that direction, and it will lower the J2S on the other satellites. So that effect the receiver might look like it's working okay. It might not even report any errors, but it will be out of position. And that effect, you want to see how bad that effect is. Okay, I've heard of trials where they've done those kind of things, and receivers have moved maybe up to 100 meters out of position without any errors being reported. So this is a diagram to try and show that jamming effect. You can see here, this is the vehicle is going around this way. This is the first jammer transmitter here. So this is jammer's located here. So as the vehicle comes around, when it gets to about here, suddenly the signals start to hit. So the receiver's relatively resilient until it gets quite close. Then it starts to jump away. You can see part 2 here. It's really being affected quite badly by the transmitter and causing errors. And then it takes a while to get back on the path and lock back on, and then it will continue on its way. So these are the kind of effects you will see on a receiver as you move in and near and away from jammers. Okay, so let's have a quick look at the software, and hopefully this will work okay. So this is a simulation. You can see here I've set up 2 outputs, 2 RF outputs. The first one here is the GPS L1 signal and the GLONASS G1 signal, and the second one here I've set up as an interferer between the, based upon those frequencies. With this, I can either select an actual frequency here and type in a number, or I can choose, what I want to interfere with. So here I've just picked GPS L1. You can see it's set the frequency to the L1 frequency, and then if I add GLONASS, which is a high frequency, you see it's taken the average of the 2. I switch off the GPS, then it puts up at the center frequency of GLONASS. Okay, say okay on that. So we're all ready to go there. If I look at the vehicle motion here, you see I've created a circle where it's going around in a trajectory. Okay, so the trajectory is going round and round. If I go and look at the interference, you can see I've got 2 transmitters. First transmitter, the signal is a chirp signal, okay, and its trajectory is fixed, and it's located relatively close to the receiver. And then if I go and look at the second transmitter, you can see that's a BPSK signal, and again, it's not fixed, it's not moving at all, it's in a static position. If I edit that, put a fixed location, again in the vicinity, slightly different, oops, slightly different location, but relatively near, and then use that location, and then we can do that. So if we're ready now, I can start this scenario, and you'll see here we've got the simulation. If we look on the map, you can see the first vehicle coming around here. Transmitter 1's on, and it's affecting it. As it gets nearer, you'll see that the power of this one is going up. And as it gets closer, and as it moves in, you'll see it will move quite rapidly. And it goes up quite rapidly, particularly now in this phase where it's quite close. See the power of the jammers going up. Even gone off the top of the screen there. And then as we move away, you'll see the power come down. Okay. So I'll just give you a quick idea. And here you can see the GPS R1 signal, and here you can see the GLONASS signal. So I'll stop those, and then we'll go back to the slides. Hopefully they're back now. So that's gives you an idea of the sort of effects you want to do with jamming and the sort of things you can do with the simulator. So let's have a look at the advanced jammer benefits. Okay, so it's got a very good J2S. So if you look at a lot of people, if they're doing the type of jamming where they're using embedded or internal signal processors, there's a limit on how much J2S. You know, we've got around about 110 dBs J2S per jammer, which gives you a 60 dB range, which gives you a lot of power. We can simulate hundreds of jammers because we're not limited by hardware channels. It's based upon just all in view. It's a kilohertz update rate for everything all the time, and this causes some is a benefit. So it's updating the signals the same as it's updating the signals for the GNSS. It offers motion, so you can move your jammers around, and so you can try what's happening if there's a jammer, say, in a drone affecting an area, or if it's flying alongside you in a flight in a plane. It offers transmitter antenna patterns, so that you can put an antenna pattern on the jammer. So in some areas it's got a stronger power than in others. And the other unique feature is it offers standard waveforms such as chirp, CW, and so on. But plus also, if you've got your own waveform in the form of an IQ file, you can use that and display those. Okay, so that's a quick overview of what we can do in jamming. We're going to have a look at spoofing now, which is a slightly different thing. It is a type of jamming, but it is in some ways a more sinister type of jamming. It doesn't necessarily stop your receiver working. It may put you in the wrong place. It may move your time. So we'll look at the different types of spoofing and what spoofing does. So spoofing is basically when you're trying to fool a receiver to think it's somewhere else. Okay, and what the something else is you're trying to make it do is maybe move its time, so it loses synchronization, and that would be for, say, something like communications, because communications are very synchronous these days, or to move your position, so a receiver will think it's in the wrong place. Spoofing signal usually would be broadcast from a single transmitter. So you know, if your receiver is studying it properly, the signals may appear unusual, particularly if you're moving. They will, you know, their power change will be strange compared to the real satellites. You know, they will all go up and down together, and they will move more rapidly than you would get with a normal signal. You know, being able to create that kind of effect helps you test and see how your receiver does. There is a sort of a particular type of jamming, something like meakening, where actually you're just replaying the standard signals at a higher power, and that will cause some quite strange effects, if you like. So your receiver will suddenly think it's moved location, and that has been detected in a few places, and it, you know, will cause some strange effects. And then sometimes repeaters can be a problem as well. So people can buy GPS repeaters. Usually they use them for testing things. There was an incident in a hangar in Germany where basically they were testing light aircraft GPS, and they had a repeater into the hangar, and so that they could test the GPS inside without having to go, you know, move the plane out as part of its service process. The trouble was that when the hangar was closed and the repeater was in there, that was fine because it was shielded. As soon as they opened the hangar doors, this repeated signal came out, if you like, and affected aircraft. One of the things about GNSS is that once you repeat the signal like that, then it actually puts you in the location of where the receiver for that repeater is. So in effect, aircraft that were moving down the runway, which was about a kilometer away from the hangar, suddenly thought that their GPS was telling them they were inside this hangar. So it caused some very strange effects. The interesting thing, it took quite a while to find this. It wasn't an easy thing to find. It was quite a strange effect, and it took, as I say, it took some time for it to be found because it didn't happen when the doors were closed. So, as I say, different types of spoofing. So, repeater, meakening type jamming, spoofing, is where you just repeat the signals, and apparently it's used quite often in Russia. If there's important people in buildings, they broadcast a meakening signal so that people move, you know, so that, if you like, a drone attack couldn't take place because the drone goes to the wrong place. And then you can have sophisticated spoofing, so where you can dynamically change the position of a receiver or change the time of a receiver. You might do this, say, to a warship at sea, so then it can't communicate anymore. It's lost communication. You might do it with trying to put someone in the wrong place. So you might want to move something off to some. There's even been people buying applications to run on their phone so that they can catch Pokemon in Pokemon Go. So it's, may not be bad for the people, but it's still, a way of changing things. If we look at spoofing in a sort of a high-level view, so this is, if you like, a receiver's location. This is the truth signal, and it puts the receiver here. So the spoof signal makes it think it's in the wrong place. So we have to have a different signal from that satellite being received by the receiver. And that is transmitted, if you like, from a spoofing transmitter, say here. So that will be, coming here. So the signal, if you like, is coming from this direction. The effect is to move you to the spoof position. And if you do that with a number of satellites, obviously you'll be moved out of location. If you want to think of it in a way, a simulator, GNSS simulator, is a spoofer, but not being broadcast in the real world. And if you look at the effect of this here, you can see the spoofing, the receiver's coming on its normal track. Suddenly, something like you jam the receiver, and then you apply the spoof signal. The receiver then picks up the signal, thinks it's the real signal because it's the spoof signal is louder, shall we say, than the normal one, and then so it will move off on the wrong trajectory instead of the right trajectory. Okay. So different sort of examples, you know, a receiver advertises multi-constellation, dual frequency spoof, jam, etc. Most receiver specs, with or without L1CA, you know, they are affected by a spoofer. Okay, so if you affect the L1CA code, you'll often affect the receiver. Jam and spoof would be a typical method of doing this. So you jam the receiver so it's lost. It's like it's gone into a tunnel, doesn't see the signals. And then you turn the jammer off and you turn the spoof signal on. And then it will grab the receivers to automatically go for the highest power signals. And if that's a spoof signal, you can grab it that way. It's worth trying different constellations. So what happens if GPS is saying one thing and Galileo is saying something else? Or GLONASS is saying something else. Can be quite interesting that on some receivers, because we have done some experiments on that, and some receivers, you know, when you jam or sorry you spoof the GPS and the GLONASS stays right, often the receiver report that there's a problem with GLONASS and follow the GPS signal because they like to follow GPS. Also maybe something that's tracking a target or simulating a signal close to real and then slowly pull it away, okay, taking over, sort of a little bit like we saw in the previous slide. And then, as I say, the last one is collateral damage, where, you know, the Russians have been known to broadcast a spoof signal to make people think they're in there, you know, so that you can't attack a dignitary or whatever with a drone. Okay, so those have been known to have happened. Okay, so let's do a summary. So what do Hydra SkyDial have in jamming and spoofing? So first of all, we have simplified jamming. Okay, so simplified jamming, this is included with the standard simulator. Okay, so you don't need to buy this, it's a standard product. It's included in the standard system. You don't have a position for the jammer, you just have a basic jammer. The manual power and level adjustments, you can change them, and you can simulate CW or chirp counts. Not bad for just checking, you know, what happens if you've got someone with a personal privacy device in their car. Those devices usually do a chirp signal, and you know, so you can see that. Then there is the optional advanced jamming, which then allows you to have transmitters, so you can locate where the transmitter is. You can move that transmitter. You can move the vehicle around the transmitter. You can the loss is calculated based upon the relative positions and the effects of the antennas. So it's all calculated automatically. And there's multiple jammer types. So as well as the CW and chirp, you've got pulse, BPSK, binary offset carrier, white noise, or you can use an IQ file. Okay, and then lastly, as an add-on option to jamming, you've got the option of spoofing, and that uses the transmitters from the advanced jamming to spoof a signal. Okay, so you can have multiple spoofers, but you know, you do need a license for each one. They're automatic calculation of the signal dynamics. You've got full control over the aspects of the constellation of the spoofer. So you in effect have an alternative constellation, and it supports things like repeaters and custom devices. And of course, you can try the jam and then spoof type of scenario. Okay, so that's us for today. It's been a slightly shorter session than normal. If you want any information about this, you can contact me, and there's my contact details. Or you can contact Jeremy if you need to have this information. If you don't have it, you can obviously get it from me, or we'll put it out later. Okay. Thank you for listening. Thank you for your time. Hopefully you found this interesting. Please, you know, feel free to get in touch if you need to know anything more. Okay. Thank you.
Thank you.
Okay. Right. There we go. Is that all right? We stop recording?
Sophie? I don't know, the counter's